We will continue our discussion of chapter 16, and in this video we will finish this chapter, planar kinematics of a rigid body. Now let's see relative motion analysis, velocity. Now before this we learn about absolute motion analysis. There absolute motion where the motion is dependent. Now relative motion analysis here, the motion of this rigid body here, we have rigid body in at time t, let's say t is equal to 0 second, and then I'm going to take 2 points on this rigid body, point A and point B, or two particle A and particle B here on that rigid body. And now within 1 or 2 or 3 seconds in time dt, this rigid body is going to move from here to here. Now when this body will come from here to here, is going to go first to translation and then rotation. So combination of both things, it's general plane motion, translation plus rotation. So whenever this body goes from here to here, this point A and B will go from here to here. Now new position of this point A is A bar, new position of this point B is B bar, and the position vector is dra and drb for A and B respectively. So that's the change in position of A and B. When this body moves here, it translates and rotates at the same time. This is the same body in time dt. Now if I am going to resolve this motion of this body into two components, one is translation and then rotation. So here first I am going to say that this body translated itself. It means dra is equal to dra. This is going to stay same. So that's my first part, translation. This is a two-step motion. First step, translation, and then second step I'm going to assume as rotation about fixed axis. So I'm going to assume that it came here and then at axis A it rotated with omega and alpha. So I'm going to have this motion into two steps, translation plus rotation altogether. Now here if I want to know this position from B to this new position from B to B, drb, whatever I get drb, I can rewrite that drb as dra plus drb by A. If I know the laws of vector, I can write down this drb as dra plus drb by A. So whatever drb from here to here I'll get here, if I have this triangle like this, I'm going to write down that dra plus drb by A. So what I see here is that the position of B is a combination of two things, dra plus drb by A. So here this dra represents translation, that the straight line motion, whatever the translation is, and then this drb by A, that's position of B with respect to A, this due to rotation about A. So this represents rotation. So that's your step 1 translation and step 2 rotation, and that's how I can write down new position of point B as drb dra plus drb by A. Now that's my displacement of point B. I'm going to differentiate this equation with dt because this motion is happening in time dt. So I'm going to differentiate this equation with dt, and if I do that, I'll get drb by dt, dra by dt, drb by 8 by dt. This is nothing but distance upon time. This is velocity of B, velocity of this point B from here to here. So I can rewrite that Vb is equal to Va plus Vb by A. It means if I want to know the velocity of B's entire body is rotating, and in that body I want to know velocity of this point B or particle B here on the body, on this rigid body, I can say that velocity is combination of Va, velocity of A, plus velocity of B with respect to A. So if I have this value, I should be able to calculate velocity, and that's your relative motion analysis. Velocity Vp is equal to Va plus Vb by A. So let's take a look at another example. Now let's say I have this mechanism in this crank is rotating, this BC crank is rotating like this. This has a circular motion, and this AB, this point A, has a linear motion to and fro. So you can imagine as this rotates, this will move like this, and then here I can apply this equation. I can safely say that VB, velocity of point B, is a combination of translation VA and VB by A. Whatever there will be a rotation, that will be VB by A. So here VB is velocity of B, VA is velocity of A, omega is angular velocity, and RB by A is a position of B with respect to A. And here this VB by A, I can rewrite it as omega R. So V is equal to omega R, that's what we know. So here VB by A is vector, so I'm going to write it down as VB by A is equal to omega cross RB by A, and omega and RB by A I can get it here. RB by A is position, omega is angular velocity, and I'm going to take this value and I'm going to plug it back in this equation, VB by A, and if I do that, I'll get another equation as VB is equal to VA plus omega cross RB by A, and that's my velocity equation. This is the equation. It will help me to solve these kind of problem with relative motion analysis and in which I have velocity. So here omega is vector, so I'm going to use K, omega cross K. K is because this axis of rotation is coming out of the screen, so I'm going to use unit vector K. So this omega will become omega K, and this RB by A is nothing but RB minus RA, something that we learn in chapter 12. RB by A is nothing but RB minus RA. So if I can take this value, plug it back in here, I can able to calculate velocity of B. Now let's do a problem from the book. Now what we have in this problem, this link A is coming down, and at the same time when it comes down, this link B is moving in this direction. So this is motion is like this, is happening like this here. So as this link comes down, B goes here. Link A is coming down with 2 meters per second. Link B, we have to find out velocity of this B in this direction, and that's the problem here. So here we have motion of A and B are connected. Motion of A is going down, motion of B will be in this direction. I want to find out the V. The velocity of A is given. Determine the velocity of B when theta is equal to 45 degrees. When this angle and this angle is 45 degrees, that's when I want to find out motion of B, and that's the problem. So motion of A is given. So here I'm going to draw this link, free body diagram for the link AB. So I have a link AB here, A is coming down, B is moving in this direction, and then we have some omega angular speed here. Now I'm going to use the equation to calculate this velocity of point B. I'm going to use the equation that we derived before. VB is equal to VA plus omega cross RB by A. This is the equation we derived before, and based on that we can calculate velocity of B as it moves in this direction. So VB is nothing but VA. I'm going to keep it like that. VA, I know it's coming downward 2 meters per second. Now this one is a vector equation, means that I have to use unit vectors I, J and K. So VA is 2 coming downwards, that's J, and as it is J downward minus, it is Y axis, so J, and it is coming downwards, so minus sign, so it will become minus 2J. Omega K RB by A. The RB and RA, this is the distance and this is the distance. I'm going to put it there. I'm going to put it back here, and I'm going to find out velocity of B. So here what I'm going to do is that VB is going to become VBI because VB is going in this direction. This is the X axis and positive X is going on. So positive X becomes VBI. So B equal to minus 2J for VA is coming down Y axis, minus 2J plus omega K because the axis is coming out of the screen, whatever axis of rotation is, cross I have here this RB by A is nothing but RB minus RA. So this part and this part, RB is nothing but this RB is nothing but 0.2 sine 45I in this direction, minus RA is cos 45J in this direction, upward direction. I'm going to put it like that here, minus here. Now I'm going to solve this one. To solve this one, I have this K cross I and I have K cross J, and I have this vector and a vector chart here, vector multiplication here. Once I do that, what I get is that I'm going to keep it like that, minus 2J here, and this one K cross I becomes J, and K cross minus J will become I. and I'm going to write that down. So it will become minus 2 omega sine 45j minus 2 omega cos 45i, and that's it. Once I have that, I'm going to equate coefficient from both sides. Here I have coefficient I, here I. So whatever this value of coefficient of I should be equal to VB. And there is no j here, so whatever the coefficient of j here is going to be equal to 0. So I'm going to equate the coefficient here. By equating coefficient of I and j, I will get VB is equal to 0.2 omega cos 45. This is the value for coefficient of I, and there is no coefficient, it's 0j on left hand side. So I can rewrite as 0 is equal to minus 2 plus 0.2 omega sine 45. That's it. Now our objective is again calculate VB. To calculate VB, we need to know omega. So based on this equation, we can calculate value of omega. This is one equation, one unknown. You can calculate value of omega. Whatever value of omega you will get, you're going to plug it in this equation, and then you can find out value of VB. And that's what you do. You will get omega here 14.1 radian per second. VB is equal to 2 meter per second in this direction, and you are done with the problem. This is a solved problem from the book. Make sure that you understand this equation, and then you solve it, and then you can calculate the velocity of V. There are other ways to solve this problem. This is one of the way by using this equation. Now next method, next part is instantaneous center of zero velocity. Now let's assume that this body A is rotating, is going through a rotation with some velocity alpha and velocity omega and acceleration alpha. And then I'm going to apply this. I have point A, point B, and then this is the equation that we derived before. VB is equal to VA plus omega cross RB by A. Now, for some reason, throughout this process, at any given instant, for some reason, let's assume that this VA becomes 0. For any instant, if VA becomes 0, then I can safely say VB is equal to omega cross RB by only this part, omega cross RB by A. Now, let's assume that it means that this VB here, I can rewrite it like this. It is going to be perpendicular. So here, according to cross product rule, direction of VB is going to be always perpendicular to RB by A. It means that VB will be going to this direction. So I'm going to have that perpendicular VB here. Now let's say I'm going to take two more points here, point C and point D. And as this velocity of A is 0, I'm going to apply this equation where I'll keep VA 0. And then what I get is VC is equal to omega cross RC by A and omega cross RD by A for this VD and VC, and that's what I'm going to write. So if I look at collectively this diagram, what I see that this is a 0 and I have VC, VD, all these points here. It doesn't matter where this point in the diagram or on the object. What I see that it is as if this entire body at that instant rotating at point A, and that's what important here. So what I look at it as say is as a pure rotation about point A, and that's why we call that point A as instantaneous center of zero velocity. It means at that instant velocity of A is 0. Of course, if you move on to the next instant, the velocity will not be 0, but for that instant, if I freeze the frame at that instant, velocity of A is 0, and that's why I'm going to call it instantaneous center of zero velocity. And if I can locate this IC, instantaneous center of zero velocity, I can solve the problem. So how do we do that? First of all, we have to locate the instantaneous center of zero velocity. So let's assume that there are three cases. First one is common. Let's assume that there is a rigid body going through some rotation. This point A is moving in this direction, this point B is moving in this direction. So to locate instantaneous center of zero velocity, I'm going to draw perpendicular to this point. So here, all I have to do is whatever your velocities are, draw perpendicular. So I'm going to draw perpendicular here, draw perpendicular here. Once I draw that perpendicular, wherever that perpendicular will meet, I'm going to mark a point, and that's my instantaneous center of zero velocity. And from that, I'm going to measure my distance. This one is RA by IC, position of A with respect to IC, and this one position of B with respect to IC. I'm going to mark it, I'm going to measure that position, and that will help me to solve the problem. How? You will see that later. Then there is another case. Sometimes what happens now, these velocities are not parallel here, but sometimes the velocities are parallel here. If that's the case, then the process is same, draw perpendicular. In this case, if you draw perpendicular, it will go, it will look something like this, and then join these, if you know the magnitude, join these this point, and wherever that will meet, that will be your instantaneous center of zero velocity. So it's going to meet here, and that's my instantaneous center of zero velocity. And there is again third rare case. In this case, velocities are parallel but they are opposite direction. If that's the case, draw perpendicular and join this point and join this point. Wherever it will meet to that perpendicular, that will be my instantaneous center of zero velocity, and that's the third case. First case is very common. Case 2, case 3 are rare, but it could happen. You could get velocities parallel, and if that's the case, you can use that and you can still find instantaneous center of zero velocity. Now let's jump on to the problem and let's see how this method, instantaneous center of zero velocity, is very useful to solve the problem. You don't have to go through a whole lot of process or vector analysis, I, J, K, if you know this method, instantaneous center of zero velocity. Now what we have in this problem is we have this piston D here, and this piston D is moving in this direction, right hand side, and you can imagine this mechanism. As it moves here, this BD will go like this from here to here, and or this BD will go like this, and then this AB will go downward direction. So if it is going to go in this direction, and then this AB will go like this, and then BD will go like this here. So the velocity of D, linear velocity of D, is given here, 3 meters per second. It's moving in this direction. That is given here. Dimensions are given. What it says, that block D is shown here, speed is given, determine the angular velocities of BD and AB. So this BD is going to rotate, this AB is going to come down. So I want to find out angular velocity if linear velocity of D is given. That's the problem. Now there are other ways to solve this problem. One of the simplest ways is to locate instantaneous center of zero velocity. For that, what I'm going to do, I'm going to draw a free body diagram of this BD. Here, BD, I'm going to draw a free body diagram, and then I'm going to look at velocities. So here what I see is that this D is moving in this direction, B is moving in this direction, this B like going like this, so it has velocity in this direction. Now to find out instantaneous center of zero velocity, I'm going to draw perpendicular here and here. So whatever these velocities are, so for VB, perpendicular will look something like this, and for VD, perpendicular will be look something like this, and wherever that will meet, that will be my instantaneous center of zero velocity. So here is my instantaneous center of zero velocity, and I'm going to mark it down, and I'm going to get my positions, RB by IC, position of B with respect to instantaneous center of zero velocity, position of D with respect to instantaneous center of zero velocity, that's RDIC, and that's what I get. Now once I have this triangle here like this, why we do it? Because of this equation. Now what it says, that these 2 points will have different positions, means they are going through some kind of rotation. It means omega BD, whatever the link BD, omega BD I have here, is depend on, once I have this triangle, is equal to VP divided by RBIC. That's whatever the VP velocity here, that's linear velocity of this point P, divided by this distance, and whatever velocity of point D divided by this distance. That's what I get, omega BD, and that's why we do it. This is point B, this is point D, this is BD, and then respective distance P, D I have here. This is the equation because of which we do all this part for instantaneous center of zero velocity. Once you know this equation, once you have that, all you have to do, punch in the numbers and calculate omega BD. Our objective in this problem is to calculate omega BD and then to calculate omega AB, and that's what we will do later. For the first part, we calculate omega BD. Now all we have to do is put the numbers in. This VD is 3 meters per second. I'm going to put that there, and I need to know the value of RD by IC, the length. This length, if I know that, I should be able to calculate. So this is a right angle triangle, and based on the right angle triangle, based on the trigonometry, I have this length. Based on trigonometry, I should be able to calculate this length, and once I have this length, I'm going to take this length, put it here, and then I can calculate omega BD, and you are done with your answer. So here RD by IC based on the trigonometry, this length is nothing but 0.4 divided by cos 45. This angle is 45, so that's cos 45 is equal to 0.5657 meters. So this length will come as 0.56 meters. Once I have that, I'm going to take that 0.56 meter here. 3 divided by 0.56 meter is omega BD, and that's my answer. So I do that, 3 divided by 0.56 meter, and final answer I'll get is 5.3 radian per second. And that's the answer. Then that is going anti-clockwise direction. So I'm going to put that direction here, and you are done with the problem. That's the first part. The second part, we want to find out the velocity of this link AB. This link AB is moving in this direction, and therefore I want to find out angular velocity of AB, and that's what they have asked. So for the second part here, I'm going to use the same equation that we used before based on this one. Omega BD is equal to VB by RC, VD by RD, RC. And here I'm going to see, here to use that, I'm going to now calculate, I'm going to draw a free body diagram for AB. Now A is fixed point, we don't have to worry about instantaneous center of zero velocity here. A is fixed point here, and here the equation will become omega AB is equal to VB by RB by A. We know V is equal to omega R. Based on that, omega is equal to V by R. Our omega AB, the length velocity here is whatever the linear velocity of this point B divided by 0.4, or whatever the length here is. V is equal to omega R, omega is equal to V by R. I'm going to use that. Now for that I need to know VB. To calculate VB, I'm going to use again this equation. I have already value omega BD 5.3. I'm going to take that 5.3, put it in here, calculate VB. Once I have VB, I'm going to take that VB, put it here. And once I do that, I'll get final value for omega AB, and that's what we do. So now first we calculate VB. Value of VB we will get around 2.12 meter per second. That's what you will get. So this point B is going 2.12 meter per second. Once you have this VB, take that 2.12, put it here, and you will get omega AB 2.12 divided by 0.4, and then you should be able to calculate omega AB, and that's where you will get VB 2.12 divided by 0.4 is 5.3 radian per second clockwise direction. So this is moving like this in clockwise direction with velocity of 5.3 radian per second, and that's it. That's the simple way to do a problem. This problem can be done by using vector analysis, by using this I, J, K unit vectors, the earlier equations, but this is easier way to do it, and that's what your method of instantaneous center of zero velocity is. Let's do another problem from the book. In this problem, what we have is this piston C, and it is moving up and down, and then this piston is driven by this part here, this link AB. So this link AB moves, and as it moves this link CB, and then as this link CB moves, and then this C will go up and down. So in this case, this is moving in this direction with the velocity of 10 radian per second. So it is going to rotate, the BC is going to rotate, and C will move upward direction. We want to find out what is the velocity of piston at instant shown. So you are rotating, the angle is 45 degree, velocity is given. At that instant, this angle is given 13.6 degrees. So what is the velocity of C in upward direction? That's the problem. Now to solve this problem, we are going to use instantaneous center of zero velocity. So here I am going to use this link BC, and then what I am going to do is that I am going to draw perpendicular to this point, velocity of this point B in this direction, C is in this direction, C is going vertical, so perpendicular will be horizontal, and then this B is going in this direction, so perpendicular will be in this direction. So I am going to draw this perpendicular. First for VC perpendicular, and for VB perpendicular will be like this here. So VB is going in this direction, perpendicular will be in this direction, and wherever that perpendicular will meet, that will be my instantaneous center of zero velocity, that will be my IC. Once I have that, I should be able to find out its velocities, and I should be able to find out this velocity of piston C. So I'm going to draw a free body diagram for this triangle or for this link BC, and if I do that, I'll get BC, and this is the part I get here. Now here what I see is that this is right angle triangle. If I consider this part, this is right angle, and this is 13.6 degrees. It means this angle should be 90 minus 13.6, and that's what I get. 90 minus 13.6 is 17.4 degree. Also, I have here this triangle, this entire triangle from A to IC to C all together. I have this value 45 degrees. This is 90, this is 45, this has to be 45. So I'm going to write that down, 45 here. So this one is 45 degree, this is 76.4 degree, and I know that this is the addition of all these angles is 180 degrees. So I'm going to subtract 100 to get this angle. I'm going to say this angle 180 minus whatever the sum will, I'll get this angle. So that angle will come 58.6 degrees. That's what I get here. Once I have that, my objective is to calculate VC. To calculate VC, we are going to use this equation. Remember why we do this instantaneous center of why use this method of instantaneous center of zero velocity is because of this equation. BC, angular velocity of BC is nothing but omega BC is equal to VB by RBIC is equal to VC divided by RCIC. So I have VC, BC here, BC here, BC here. So whatever VB divided by this distance, whatever VB here divided by this distance, whatever VC here divided by this distance. And my objective here is to calculate VC. Now here to calculate VC, we need to know either omega BC or we need to know this VB, and also we need to know these distances, whatever the distance in length, we need to know that. So the first part, this VB, V equal to omega R. So this VB is nothing but omega into this R. So this is given. So this is moving like this. So this is given. Based on that, I should be able to calculate linear velocity of point B. And that's what we do. VB is equal to omega AB into 0.25 feet, whatever these distances are. It means VB is 10 into 0.25, and that's how I can calculate VB. Once I have that, once I have the value of VB, I need to know this value, I need to know this value, and once I know that, I should be able to calculate VC, and that's the problem here. So to calculate these two values here, RB by IC and RC by IC, RB by IC, RC by IC, this and this length, I'm going to use the geometry. Here I'm going to use something called as law of sines. Law of sines says that if you have any triangle, you know the length, you know the angle. If that's the case, then sin A by A, sin B by B, sin C by C. This is something that we are going to use for this triangle, and if you use that, you can easily calculate. If you know angles, you can easily calculate RB by IC, RC by IC, and that's what you do. All you do is that now you have this one length, you know this angle 45, you have 0.75 feet here. I'm going to put that there, and based on that relationship, I'm going to calculate this part and this part. And once I have that, I'm going to take that value here, this value here, and then I can calculate VC. I already have VB here, and once I have that, I can calculate value of VC in upward direction. So all you have to do is solve this one, and then you will get final answer as VC is equal to 2.2 feet per second. That's your problem. This one is again solved problem from the book. All you have to do is find the instantaneous center, get the angles, use this relationship. Once you have that, find out VC, and that's pretty much it. 2.2 feet, it means that as it is rotating here, this VC is going in upward direction with 2.2 feet per second. And you're done with the problem. Let's move on to the next part and the final part for this chapter, relative motion analysis, acceleration. So initially, before this one, we did relative motion analysis velocity, and based on that we got that equation, VB is equal to VA plus VB by A. Now, to get an acceleration, I'm going to differentiate this equation. So the earlier example, if you remember, this body A, this body, rigid body is going through translation and rotation, step 1 translation and then step 2 rotation. So this point B, or total velocity of B to here is combination of dRA plus dRB by A, and based on that we got this value VB is equal to VA plus VB by A. Now what is the acceleration for this point P? To get that, we are going to differentiate this equation again with time, and if we do that acceleration, I will get AB is equal to AA plus AB by A. That's my acceleration. Now for this AB by A, that's acceleration of B with respect to A. I can rewrite this one. Now as it is a rotation, it is rotating, this point B is rotating. We have two accelerations here, normal and tangential components. So here this AB by A, I can rewrite it as alpha R, which I can look at it as a tangential acceleration, and omega square R, which is a normal acceleration. This is tangential, this is normal acceleration, and I can take this entire thing, this tangential and normal acceleration, I can plug it back here, and then I can get new formula for acceleration of B, which will look something like this. AB is equal to AA alpha cross R minus omega square RB by A, or I can rewrite it as simply AB is equal to AA plus tangential plus normal acceleration, and that's how I'll get this relative motion analysis for acceleration for this point B. And this is the equation, or this is the equation, I can use it to solve the problem. So let's do a problem. This is the last problem in this chapter. Now what we have here is a disk. This disk is rotating, and then this is rotating and is going in this direction. This rotating with omega 6 radian per second, alpha 4 radian per second. So speed is 6 radian per second, acceleration is 4 radian per second square, and the radius is half feet is given. Now it says that determine the acceleration of point A at this instant. Now it is going its own pace with this velocity and acceleration. What is the acceleration of this point A? That's what we want to find out. So to find out acceleration of point A, I'm going to draw free body diagram, and if I do that, what I get, this point G is moving in this direction, this point G has a linear acceleration in that direction, and then A is moving in this direction, it is rotating, and when it does, it has tangential acceleration or x directional acceleration in this direction, and then y direction acceleration, or you can assume that it is a normal acceleration in this direction. So here AA and AX. So I want to find out this value here, or I want to find out the acceleration of this point A. To do that, there are other ways to do that, but here we are going to use this equation, acceleration of point A, that we derived before. I have 2 points here, point G, point A. So acceleration of point A is given as AG plus alpha cross R AG, that's my distance here, minus omega square RA, omega is 6, RAG, again this distance here. Now this is a vector equation, this is a vector analysis. It means I have to use IJK unit vector. So I am going to put that there. Here this AG, this part AG, the magnitude of this point AG, linear acceleration, is given as alpha R. So alpha is 6, R is 0.5, it means this point G is moving in this direction with 6 into, with alpha is 4 actually, alpha 4, R 0.5, 4 into 0.5 is 2, so I'm going to put that here. Linear acceleration of this point G is 2 feet per second square. I'm going to need that here. I need to know the magnitude of this G. So for that I'm going to calculate magnitude 2 feet per second square. That's a linear acceleration of this point G. I'm going to put it there. And now I'm going to use this equation in the vector form to calculate the acceleration of A. Now to do that, acceleration of A is equal to minus 2I, this AG, this point G is moving in this direction. That's my negative x, and that's why minus 2I plus 4k. Alpha is 4 and k is because this axis is coming out of the screen, that's my unit vector, so I'm going to use for alpha 4k cross RA by G. So this RA by G is position of A with respect to G is going downward, so I'm going to use minus 5j. Minus 5 is a distance, J is y-axis, and minus sign is because the position is in downward direction from point G, so minus 5j. That's done here. Minus omega square RA, omega square RA by position of A with respect to G. So omega is 6 square minus 0.5 j. So minus 0.5 j is position stays constant. Now once you're done with that, our object is to calculate acceleration of point A. To do that, I'm going to use this vector multiplication, and based on that I'll calculate k cross j, and then yeah, that's it, k cross j. I'm going to calculate that, and then I'll get here minus 2, I'm going to keep it like that. This k cross j will become I, and this is 4 into 0.5 will become 2. So I'm going to write that down, and then I'm going to keep it like that here for the 6 and minus 0.5 for now. Now if I look at it, what I see is that minus 2 plus 2 cancel each other out. So I'm going to cancel that out. It means acceleration of A is equal to 6 square into minus 0.5 j, and I have already minus sign here. So that minus and that minus will become plus. And what I get is that acceleration of point A is 18 j feet per second square, and that's it. Now 18 j here, we have 18 j, it means that it's going to be positive, that's your magnitude, and j is a direction, feet per second square, and that's your acceleration of point A, and that's the final answer for this problem. Now this is the problem solved with two different methods in the book. This is a solved problem from the book. So this vector method is slightly difficult method. There is another method, is a scalar method. Now if you are reading the book, I strongly suggested you go through both of this method. This is one method, you should know it. Learn your scalar method, and that scalar with you'll get magnitude as 18 feet per second. So you'll get same answer without j. So go through this problem in the book and go through all the problems, all the solved problem in the book. And when you do go through them, don't read the problems, understand the problems, take pen, paper, calculator and solve these problems. And that's it. That's your last problem. Relative motion analysis for acceleration. Final answer we'll get here is 18j, and you are done with it. Do this problem again from the book. I'll stop here right now. That's the end of chapter 16, and we will continue in our next video. We will start at chapter 17. All right, you stay safe.